Hello, ladies and gentlemen. First of all, let me introduce myself. My name is Rezeda Khaydarova, and I'm a PhD student at University of Information Technologies, Mechanics and Optics. I'm from Russia, St. Petersburg, and I would like to introduce our research, RockCNN, a distributed RockPro64-based convolutional neural network cluster for Internet of Things, verification and performance analysis. So, why did I choose this topic? First of all, I would like to admit that Internet of Things-based technologies became an indispensable part of our daily life. Number of IoT devices is increasing in a fast pace. Moreover, IoT devices often require online functionality where data is analyzed by means of machine learning or deep learning techniques. For instance, security camera can be used for recognition, strangers in the house, or unattended objects left in subway or airport. Convolutional neural networks have been intensively researched and used in a large-scale data processing because of their comparable classification accuracy. But executing CNNs locally on mobile and embedded devices require large computational resources, great memory, and power consumption. So what can we use to execute it on real time? Maybe we can use supercomputers or classic clusters? Yeah, it's a great solution for it, but they consume a lot of energy. They are expensive and take a lot of space. So another option is to use single board computers, but it's relatively new trend. For example, first Raspberry Pi was released in 2012, so it is possible to organize cluster with single board computers. Thus, the motivation of our work is to organize distributed convolutional neural network in the single board computer cluster. Here, a RockPro64 cluster is presented. We have this cluster in our laboratory only after New Year. The name of our laboratory is Information Science and Semantic Technologies. The cluster consists of 24 RockPro64 single-board computers. In our experiments, we use only 22 nodes. There are 3 levels in a rack, you can see, and in each level 8 single-board computers are located. The main goal of our work is to deploy distributed convolutional neural network in single-board computer cluster. So in development pipeline, some steps are presented. First of all, we reviewed use cases of single-board computer cluster and reviewed some models and algorithms for distributed convolutional neural network. Next step is developing a preliminary architecture. Moreover, it's necessary to test the performance of our single-board computer cluster, to know some metrics for further researches, and to compare it with existing single-board computers. Then 3 use cases are conducted: face recognition, sentiment analysis, and time series data. In each step, we are preparing dataset and we are training the model. Architecture development is an iterative process, so we need to make some corrections in each step. To distribute the CNN, scheduler is need to develop and CNN partitioner. When, of course, it is necessary to test the performance and to make some conclusion. So in each case, steps are the same. Finally, according to results, direction of future development are discussed. The proposed 4-layer architecture is based on our previous work that was done for semantic technologies and IoT. Here we changed it for CNN, the architecture of the system called RockCNN. The first layer is a data collecting layer, so various IoT devices such as video cameras or different kind of sensors, smartwatches, etc. generate a flow of data that needs to be analyzed to be applied for other tasks. The second layer is a lightweight analysis layer where some services filter the data to fit the data type and inform the source devices if data is not recognized. All the data recognized as relevant is analyzed in RockPro64 cluster. So the next layer is a data management and processing layer. Core manager, it's a head node, accepts structural parameters of CNN model as input and provides them to CNN partitioner. A CNN partitioner distributes the tasks, local tasks, and gives them to the scheduler, and scheduler distributes tasks among the nodes. So as soon as all the nodes have done processing, results are collected, merged, and they sent to core manager. So here also in the processing stage, some CNN frameworks like DeepThings, TensorFlow, MXNet, and others could be used. So the last layer is presentation layer. We have organized the layer to represent the results of 3 use cases. It's object recognition, sentiment analysis, and time series data. So the results are presented in the last layer. Face recognition is one of the use cases of CNN model. Here, CNN architecture of object detection is presented as an example. It may have numerous layers such as convolutional, subsampling, it's a pooling layer, and another fully connected, for example, layer, etc. So it can be different, it depends on various conditions. The general CNN model for sentiment analysis is shown here. First of all, sentences that need to be analyzed are transferred into a matrix. The rows of each sentence matrix are represented as a word vector. We perform convolution in the matrix, applying filters. After that, maximum pooling function is applied to each feature map. Finally, softmax function consumes the vector from a fully connected layer and produces result as a positive or a negative sentiment output. So here also you can see an example from IMDb, user reviews that are leaving some comments. A large diversity of data is stored in a time series format. Those are climate control measurements, medical test results, etc. They can be used in a variety of applications as a forecast and disease prediction source. Researchers have proved that convolutional neural network can be used in this case also. On the transformation stage, various functions are applied to input time series data, such as smoothing, discretization, etc. In local convolutional step, convolution with different filter resolutions is applied and the maximum pooling is used. Every convolutional layer is followed by a maximum pooling layer. During the full convolutional step, all the outputs of previous stages are concatenated and more convolutional and maximum pooling layers are engaged. Then results are merged and to form a flat vector which is used as input to a layer connected to softmax function. So as a result, a predicted distribution is formed. Comparison table of Raspberry Pi 3B, Android C2 and RockPro64 is presented here. Most of the research works are comparing Raspberry Pi models with Android C2 and others. A comparison of RockPro64 with other single-board computers is not discussed in research yet. RockPro64 is a 64-bit computer built on a Rockchip 3399 hexacore system on chip, integrating a dual-core ARM Cortex-A72 and 4 quad-core ARM Cortex-A53. We've provided with a quad-core Mali T860 MP4 and up to 4 GB of system memory. It's more expensive than a Raspberry Pi, but the characteristics are better. RockPro64 cluster's performance was tested using high-performance Linpack tests. It is a portable and open-source software package that enables to test the dense linear systems to measure the floating-point operations per second on distributed memory computers. It was chosen as a widely used and freely available software supporting most of the relevant systems. It includes vector operations, matrix-vector operations, and matrix-matrix operations. Generating a configuration file according to characteristics of RockPro64 as an example is shown here. We compare the performance of RockPro64 with Raspberry Pi 3B Plus and Android C2. Raspberry and Android was tested on 16 nodes. The maximum performance of RockPro64 cluster when it has 22 nodes is 100 gigaflops. Compared to Raspberry Pi, RockPro64 is twice more powerful. All measurements stop at 80% memory usage because of some random access memory resources are required for the operating system. During testing the RockPro64 cluster, the temperature was measured with a rate of 10 seconds. In the first figure, we compare two nodes, master node nearest to coolers and the node located on the opposite side far away from coolers. During the first 15 minutes, the coolers were turned off and the tests were running, so the maximum temperature of master node is about 80 degrees. But compared to another node, the temperature in the master node rises drastically because of running additional tasks. Coolers are turned on 15 minutes later. The master node temperature drops dramatically compared to node 18 due to its location. A comparison of two nodes compared to the master node is presented in the second figure. Within the first 15 minutes, node 18 and node 14 behave differently as far as temperature is considered. Node 14's temperature is increasing dramatically. The reason is that the nodes are not balanced and not optimized for parallel task processing, and an appropriate load balancer has to be configured and used to schedule and distribute the tasks equally. In the figure is shown the average temperature of CPU in each node for 3 hours. The scheme of location of each node is presented here also. Every level has 2 coolers. The maximum temperature is 52 degrees and the minimum is 42 almost. Average temperature of nodes that are near the cooler is less than others. For example, node 14, which is near the cooler, so the temperature for node 14 is 43 degrees. The risk of destruction is 125. So it means that coolers are working properly. The memory footprint of each node is presented in figure. Every node was tested within a different memory consumption percentage configurable in the configuration file prior to running the tests. A current maximum of 22 nodes consuming 80% of memory has shown the performance of 100 gigaflops. All the nodes have shown the performance of 80 gigaflops when the 20% memory is used, so it's displaying a fair rate of efficiency. So to sum up, we already designed a preliminary RockCNN architecture. We presented 3 use cases of CNN model. Moreover, RockPro64 cluster performance was tested and compared to other single-board computers. So in future, we need to enhance our RockCNN architecture. We need detailed work with 3 use cases. We need RockCNN scheduler and load balancing development. And of course, we need to test it and verify. Thank you for listening. See you next time. Goodbye.